Hello friends, today we are going to discuss about the setup time and the hold time considerations. Supposedly the setup and hold are a big mystery in electronics. Let's see if the smiley remains till the end of this demo. What is actually the definition of a setup time? Setup time is the minimum amount of time the input must be stable before the clock edge. The hold time is the minimum amount of time the input must be stable after the clock edge. Okay, reading through this definition, you might be thinking, what is this input and what is this clock edge? Input is the input to any kind of circuitry. So, where did this clock come from? Okay, now, like the basic question should be, what is the clock edge? And where is the clock in the definition? And is this limitation present only for combinational logic? Is it not for sequential logic? The very basic questions, what are these and why do these conditions arise? Okay, let's see. Before going to answer these questions, let's understand why does the setup condition arise. If you consider any transistor circuit, it would basically have an input capacitance as seen from the input terminals like this. It would have an output capacitance as seen from this side. So whenever I input a signal V in, suppose I connected a DC voltage, the voltage would come and get charged this input capacitance. Whatever voltage on this capacitor is present is what is seen by this transistor input. So, and similarly, when an output has to appear for this corresponding input, the transistor should operate in the mode of operation according to the voltage input like active, saturation or cutoff, and correspondingly it will charge its output terminal to provide the desired output voltage. So when my input is present like this and a clock is being input to the circuit, so the setup time for a circuit is, as per the definition, is this much amount of time minimum this input should be stable. Say this is in state 1 or logic high, it should remain high for at least this much amount of time so that my transistor or my input circuit would see it as a 1. So what is the hold time? So for my circuit to operate and provide a reasonable output and charge the output capacity, at least this much amount of time the input should be present so that the valid output corresponding to this input would be appearing on my terminals. So what will happen if my setup is violated? Okay, see that here is a setup time in between which my input signal is switching from 10 10 10 really fast. So if my input is in this fashion, my peak voltage is this much. So we know that there is a capacitor at the input terminals. So what happens if I apply a square wave? It goes on linearly charging. It integrates this voltage. So this is the voltage my transistor input terminals would be seeing. So what if sufficient amount of time is not there for the capacitor to charge to full voltage? So before the capacitor charges to Vin max, we are charging and discharging it real fast. So what will happen is the transistor sees the input as an integrated voltage over a period of the setup time. So what should happen ideally? Ideally, when an input is applied, the input on the capacitor should charge really fast. It will charge really fast, but this much amount of time for which it takes to charge is generally defined as setup time. So at least this much amount of time, if my input is not stable, the voltage here is not going to be a complete maximum or a complete charged value which would be read at the clock edge. So if the clock is present, the clock will read whatever is present at this instant of time. If my clock occurs in this interval, it would read something, an average value over the integrated period of time. So here is something we have known. So during setup violation, the input is perceived as an average voltage value on the input capacitor. The average voltage value is obtained by V input integrated over the setup time. So this value might be a metastable value, which means supposedly my circuit should be operating in, if it's a transistor circuit and I am switching between logic 1 and logic 0, my circuit should be operating between saturation and cutoff. So when I apply a 1, it's an NPN transistor, ideally output should be 0. When I apply a 0, the output should be 1. But if my input is switching so fast, my transistor will see that input as a average of 1 and 0, which might be a logic value which will lead to active mode of operation of the transistor. So the voltage would be accordingly a linear amplification of the same, or whatever is the transfer characteristics of the transistor defined. So in this case, we can't guarantee the mode of operation of any circuit. So these values are defined as metastable values. These are basically due to undesirable, or these will lead to undesirable outputs, changing the mode of operation of transistors. So why do we need the hold criterion? So if a transistor input is gradually changing, and accordingly the output of the transistor would change, right? So if the output is changing, the output would change according to transfer characteristics of the transistor defined. Say if it's a current controlled current source, a BJT, the output current would be a linear amplification of the input current. If it's a voltage controlled voltage source, the output voltage would be a function of the input voltage. So accordingly the output voltage would, but for that output voltage to appear on Cout, accordingly it would take some amount of time for the Cout to get charged. This amount of time is what is defined as the hold time. So if the hold time violation occurs, that means if we change the input intermediately, the output on the circuit would also be changing. So whatever is the value on the output capacitor would get integrated over the period of hold time. This would lead to a metastable voltage at the output. If this output is fed as input to the consecutive stages, the entire signal chain would be operating erratically. So if we list out or condense what are the findings we have found till now, the setup criterion is not met, the metastable values are seen at the input, which could give an undesirable operation. If a hold condition is not met, metastable values are seen at the output, and the entire signal chain would be erratic if the output is fed to next input stage. So what would limit? What limitations does a setup and hold put to us? They obviously give an undesired mode of operation, but still, if we see the maximum frequency of operation is limited. If my input signal is changing very fast, my circuit can't see the input changing at that frequency. So it basically limits the maximum frequency of operation of the circuit. So consider the D flip-flop. D in is the input, Q is the output. It's the clock. It's a positive edge flip-flop, suppose. And the setup time is 10 nanoseconds, hold time is 8 nanoseconds, and delay is from D to Q, combination delay is 20 nanoseconds. So how do we find the maximum frequency of operation? Ideally, my input should be stable for T setup before the clock edge. My input should be stable. We can see here. My input should be stable for T setup before the clock edge. My input should be stable THT after the clock edge. So this is the minimum amount of time my input can't change. During this time, the input value, whatever it is, should remain as it is. So after this, one more change may occur. After this, a change may occur, but it would also be something following this condition. So the maximum frequency of operation would be 1 by TST plus THT. But ideally, this is not what happens. So what actually happens is, if I have a circuit, it will have some combinational delay which might be greater than the hold. So for the first time when my output is occurring, due to the combination delay, for an input at t equal to 0, my output will occur at t equal to 20 nanoseconds. So the output gets charged before my because my hold value is only 8 nanoseconds, the output capacitor would get charged in this interval. So there is no problem of hold limit. So what is limiting here is the propagation delay of the circuit and not the hold time. So in this case, the mean frequency of operation would be 1 by t setup plus 1 by d2q propagation delay. This is what we have to consider. We have to consider the maximum of hold time and combination delay to find out the worst case maximum frequency. Okay, analyze the circuit. What's going on here? Okay, the D and the clock inputs are shorted. So my clock would be exactly the clock, exactly same as the input. So at my clock input, the setup and hold conditions are not met. So the flip-flop is going to operate in metastable switch. Okay. Enough for the setup and hold theory. Now you can analyze these things. Ideally, clocks are not perfect square waves. So what will happen to set up, hold them? How are the conditions going to change? The edge of the clock, the clock would
Yeah, so these are the conditions one should explore. Okay, just a minute. Okay, explore more. Yeah, ideally clocks are not perfect square waves. So what will happen to set up hold them? If the clock is changing between two stable levels. So whatever is the 50% point during the rise of the clock should be considered during the low to high or high to low transition is considered as the edge of the clock. So from that point, 50% point time, we should ideally estimate the setup condition. So the clock value would be sampled the value would be sampled at the input would be whatever is at the 50% time 50% of the rise of the signal. So accordingly, the rise time of the square wave should be rise time of the clock should be considered for finding out the setup and hold. Okay, is there a limitation between setup and hold and sample and hold in analog? Yeah, I think one should analyze this. The transistor operates on the same condition. If the transistor's inputs are changing real fast, it would integrate. So sample and hold are something a bit similar, yet there are some subtle differences. This is a nice assignment to do. So why do we need hold circuits at all? Once we have calculated a value, we can pass on that value into a next circuit or another capacitor, so that this value is not corrupted due to the changing of the inputs or the unstable inputs. So this is what you do in a hold circuit. One can relate to the slew rate from the above theory. Bye. Thank you.